Bismillahirrahmanirrahim, dear students. I am Hamad Abbas, your host. Welcome to all of you from the platform of Quanta Publisher. Today, our topic is about the rectangular components. Last time we studied about a product of vectors, addition of vectors, subtraction of vector, unit vectors, and so on. Now, today, we will discuss about the rectangular components. First of all, we will define about the rectangular components. Let we draw a plane here. Suppose there is a vector A and we draw projection from the head of vector A on x-axis. Now we will label this one as a horizontal component and we will write here AX. Similarly, the vertical components here, this one, we will label here AY. Now, let here is angle theta. This one. We can see here from the diagram, this component AX is along x-axis and AY is along y-axis. This is also AY here. If we discuss above from the definition of equal vectors, if here is AY, there is also equal to this one, AY. We can see here, these two components are at right angle to each other. That is, the angle is 90 degrees. So we call these two vectors as rectangular components because they will make a rectangle almost. You can see here, vector A have components AX and AX, AY, and this one is also AY. There is a rectangle. These two components are combined by head to tail rule and give a rectangle. That's why we call these two components as a rectangular components. There is another definition of rectangular components of vectors. The components which are mutually perpendicular to each other are called rectangular components. From figure we can see here like this one. This is an example of three-dimensional case. Here is along x-axis and we label as AX component. This one is AY and y-axis, y components. And this one is along z-axis and label as AZ component. From head to tail rule, the resultant of vector A is equal to the combination of AX, AY and AZ. You can see here this one. Now, if we want to describe these components with direction, then it is necessary to denote these components with their unit vector. For example, AX is along x-axis, its unit vector, its direction is along x-axis is labeled as a unit vector, and y component labeled as AYJ and z component AZK. In case of magnitude, we will scale AX component, AY component, and AZ component. Because unit vector have magnitude 1, that's why square of 1 is also 1, and we do not write here 1. So simply A is written as AX square plus AY square and Z square under root. These were the basic definition and some formulas regarding about the rectangular components. From diagram, we can also interpret cos theta, sin theta, and tan theta also. We have read in the previous classes here. No need to rewrite these formula again. Now the direction cosines. Direction cosines actually are the angle of cosines which are made from the horizontal axis. with their respective angles. For example, alpha with the x-axis, beta from the y-axis, and gamma along the z-axis. From diagram, it is clear that this is a vector A, and the angle from x-axis is alpha, angle from y-axis is the beta, and angle from z-axis is the gamma. So these three angles are termed as direction cosines if we take their ratios with the hypotenuse at the base. For example, from the definition of unit vector, we know that a unit vector is obtained by dividing a vector with its magnitude. So we use this value of vector A from here to this one, and we will got this one. Now separating these components with the each magnitude, and we will get this ax over ai plus ay over az over ak. You can clearly see here from the diagram ax over a, that is the base, and this one is the hypotenuse. So hypotenuse, base over hypotenuse, that is equal to cos alpha. Similarly, base of vertical component over vector A hypotenuse is the cos beta, and the hypotenuse ratio with the base component of z is called cos gamma. So you can write here this one is equal to ax over a cos alpha, and this one is equal to cos beta, and this one is equal to cos gamma. Where cos alpha, cos beta, and cos gamma are termed as the direction cosines of vector A, and they are denoted by. These are the conventional signs in the mathematics. Sometimes cos alpha is written as with L or denoted with L, cos beta with M, and cos gamma with N. So this equation, here we will write L, here we will write M, and here we will write N. That we will get this equation L, I, M, J, and N, K. Similarly, if we take the magnitude, then both sides, this will equal to L square, M square, N square. And this one is a unit vector having magnitude 1. That's why we write here equal to 1, this one. And if we take the square, L square, M square, N square is equal to 1. In the exam, mostly, this question is written in form of the derivation. Show that sometimes students ask to show that L square, M square, N square is equal to 1. It means that the examiner is going to ask about the direction cosine of the vector A or any vector irrespective of A. So these was the two fundamental identities of vector, which terms as rectangular components and the direction cosines of the vectors. Now we will discuss about the vector derivatives. In the mechanics, vector is a quantity which is used to describe the direction. That's why its derivative is also important, because the derivative of vector give somewhat new quantity. For example, the velocity is defined as rate of change of displacement, and acceleration is defined as rate of change of velocity, and so on. Now consider a particle from position here P1. This is labeled as position 1, and this is labeled as position 2. If a particle moves from position 1 to 2, then its position vector is noted by R1 and R2, and delta R is the change in position. From head to tail rule, we can see here the sum of R1 plus del R is equal to R2, or R2 can be written as, delta R can be written as R2 minus R1. Similarly, if these 2 points where we label here P1 and P2 are so close to each other, it means that there is a smallest interval of time to reach the particle from position 1 to position 2. And time interval is taken as delta t approach to 0. That is called instantaneous value of the position. Now we will write here delta limit delta r over delta t, that is equal to the velocity. So simply rate of change of displacement is equal to velocity. To find the acceleration, we will again take the derivative of velocity. The rate of change of velocity is called acceleration. And if we write here v, that is equal to dr over dt. So this is equal to double time rate of change of displacement is equal to the acceleration. Where conventional unit vector r is denoted as xi, yj, and zk. Or in simple case, r is a vector that is equal to magnitude product of magnitude and direction. Now the time derivative for the limiting case by using the first principle can also written as, if this is equal to dr over dt, then r t plus delta t minus r divided by delta t. So this is the simple case of the limits. When we replace t as t plus delta t, or using this equation from r here to here, then this r is equal to the magnitude and direction. Similarly here, r is equal to magnitude and direction. Then separating the variable and divide these quantities, we will get this equation r dr over dt and dr over dt into r. This is equal to, this one is equal to the velocity, and using the product theorem, we will get this equation and label here 1.7. Remember that if one of the quantity is a scalar and another is a vector, then this is equal to the simple multiplication, not dot or cross product.